On a calm afternoon in an English orchard long ago, a young Isaac Newton sits under an apple tree. The air is still and warm, and not a sound disturbs the peaceful scene. As Newton rests in quiet thought, he notices an apple detach from its branch and falls softly to the ground beside him. He gazes at the fallen apple and wonders deeply, why did it fall straight down to the earth rather than drifting sideways or floating upward? In that serene moment, Newton's curiosity about the falling apple sparks a gentle revolution in understanding the world. He begins to suspect that an invisible force pulls the apple toward the earth. He imagines that perhaps the very same force drawing the apple to the ground also reaches up to tug on the moon, keeping it circling in its orbit above. Newton calls this unseen influence gravity, and in the stillness of that orchard, the concept of a universal gravitational pull is born. It is a simple, profound insight. The quiet fall of an apple and the majestic dance of the moon obey the same natural law. In the years that follow, Newton quietly develops a set of simple rules to describe motion and forces, rules that would become the foundation of classical physics. He finds that objects naturally stay at rest or move in a straight line at constant speed unless a force acts on them. He observes that when a force does act, it changes an object's motion. Push twice as hard, and you get twice the acceleration. Push a heavy object, and it accelerates less than a light object with the same push. And he notes that forces always come in pairs. If you press your hand against a wall, the wall presses back against your hand with equal strength. These principles, later formalized as Newton's 3 laws of motion, elegantly describe how things move in our everyday experience. A rolling ball on a level surface will keep rolling straight and steady until friction, a force, slows it to a stop. A heavy cart requires a strong pull to get it going as fast as a light cart. And if you jump off a small boat, the boat gently drifts backward as your body moves forward. A subtle reminder that actions have equal and opposite reactions. In Newton's view, the world runs on sensible rules. Forces cause changes in motion, and without forces, an object would simply continue doing whatever it was doing. This understanding paints a reassuring picture of nature as something orderly and predictable. Newton's insights into gravity and motion form only part of his legacy. He is also fascinated by light. In a darkened room, Newton performs a quiet experiment. He lets a thin beam of sunlight enter through a small hole in his window shutter and pass through a glass prism. To his delight, the beam fans out on the opposite wall into a beautiful spread of colors, a rainbow painted by sunlight. Newton discovers that the white sunlight is not pure at all, but actually made up of all the colors of the rainbow mixed together. By recombining these colors with a second prism, he shows they merge back into white light. This revelation that white light contains a spectrum of colors is a profound insight into the nature of light. In that dim room, the wall aglow with gentle bands of color, one can imagine Newton smiling softly at the realization that something as commonplace as sunlight hides a rich complexity. This work lays the groundwork for optics, study of light, and it demonstrates Newton's patient, thoughtful approach, using simple, clear experiments to uncover nature's secrets. Newton's prism experiment is one of the earliest scientific studies of light, and it raises new questions. What is light exactly? Newton, with his particle-like corpuscular theory of light, and others like Christian Huygens, who think of light as waves, set the stage for a long debate. But the answer will gradually become clear in the generations after Newton, through the work of many others investigating electricity, magnetism, and the nature of energy itself. As the 18th and 19th centuries unfold, the gentle quest to understand nature continues. A new kind of invisible influence captures scientists' attention: electricity and its close relative magnetism. People have noticed for centuries that certain materials like amber rubbed with cloth can attract lightweight objects, or that lodestone rocks can nudge compass needles from afar. These phenomena feel almost magical and unrelated to the clockwork physics of Newton. Yet, quietly, experimenters are beginning to tease out their secrets. In laboratories lit by oil lamps and curiosity, scientists explore how electricity can flow and how magnets can induce motion. In a modest basement laboratory in London in the early 1800s, a bookbinder's apprentice turned scientist named Michael Faraday conducts simple, elegant experiments that reveal a profound unity between electricity and magnetism. Faraday is a humble, curious man who often works by candlelight, patiently observing nature's subtleties. In one famous experiment, he coils two lengths of wire around opposite sides of a circular iron ring. When he passes an electric current through one coil, he finds that a momentary current is induced in the other coil, as if the electrical influence leapt through the iron ring to the second wire. In another experiment, he discovers that moving a magnet in and out of a coil of wire can create a tiny electric current in that wire. He connects the coil to a sensitive galvanometer, and in the hush of his lab, sees the needle flicker whenever the magnet slides in or out of the coil. With these gentle experiments, Faraday demonstrates electromagnetic induction. A changing magnetic field can induce electricity. It is a quiet, yet groundbreaking discovery. It means that electricity and magnetism, which once seemed separate, are deeply intertwined, two aspects of a single phenomenon. A dancing magnet can generate an electric current, and as others will soon find, a changing electric current can produce magnetism. Faraday's work shows that invisible lines of magnetic force can carry energy across space, generating electricity without any physical contact. In time, this principle will be used to build the first electric generators, where coils of wire spin in magnetic fields to produce the electricity that lights our homes and powers our modern world. A direct outcome of Faraday's curious tinkering. Years later, building on Faraday's insights, the Scottish physicist James Clerk Maxwell takes the next leap. In the 1860s, Maxwell develops a set of equations that unify electricity, magnetism, and even light. He predicts that light itself is an electromagnetic wave, essentially a ripple of electric and magnetic fields oscillating together, traveling through space at the speed of light. According to Maxwell's theory, whenever electric charges accelerate, for example, when an electric current oscillates in an antenna, they should send out waves in the surrounding electromagnetic field. These waves move outward at a fixed speed, about 300,000 kilometers per second, and Maxwell calculates that this is exactly the known speed of light. It is a breathtaking unification. The warm glow of sunlight, the red flame of a candle, the invisible waves from a radio antenna, even the colors Newton saw spread out by his prism. All are electromagnetic waves, differing only in their wavelength. Maxwell's prediction is soon confirmed by experiments, notably by Heinrich Hertz in the late 1880s, and the idea that light is an electromagnetic wave becomes a cornerstone of physics. Imagine the satisfaction of this realization. The gentle light illuminating a quiet room and the unseen radio signals passing through the night are fundamentally the same kind of wave, both part of the grand electromagnetic symphony of nature. The once disparate threads of electricity, magnetism, and optics are now woven into a single tapestry. While Maxwell is bringing light into the fold of electromagnetism, other scientists are delving into the nature of heat and energy, founding the field of thermodynamics. Every time you boil water for tea or feel the warmth of a sunny window pane, you're experiencing thermodynamic principles. In the 19th century, during the age of steam engines, understanding heat, how to convert it to work and vice versa, becomes a pressing question. In laboratories and workshops, researchers like James Prescott Joule, Rudolf Clausius, and Sadi Carnot carefully measure and ponder the relationship between heat, work, and energy. In the quiet English countryside, James Joule performs a particularly telling experiment. He sets up a device with a paddle wheel submerged in a container of water, attached by strings and pulleys to heavy weights. When the weights are released, they very slowly fall, turning the paddle wheel and stirring the water. It's a very gentle process. No splashes, no noise, just a controlled plodding of the wheel through water. After the weights have descended and the water has been churned for some time, Joule measures the water's temperature. He finds that the water has warmed up ever so slightly due to the stirring. In essence, the work done by the falling weights, a form of mechanical energy, has been converted into heat in the water. This was a striking demonstration that mechanical energy and heat are different forms of the same thing. Energy, Joule suggests, is conserved and can change forms. Here, from the energy of motion, weights dropping, wheel turning, into the energy of random motion of molecules, heat in water. In modern terms, this is the first law of thermodynamics, the principle of energy conservation. The total energy remains constant, merely changing from one type to another. Joule's experiment, performed with patience and precision in tranquil settings, gives us a comforting message. The universe doesn't waste energy. It keeps track of it, converting it from form to form. When you wind up a clock spring, then the clock ticks and the spring unwinds, that stored energy turns into motion and a bit of heat. When you rub your hands together on a chilly night, the mechanical work of rubbing turns directly into warmth that you feel on your skin. Energy is like an unchanging substance that only swaps costumes: kinetic, thermal, chemical, electrical, but the amount stays constant, an unbreakable accounting. Scientists also discern a further truth about heat. It has a natural direction of flow. If you leave a hot cup of tea on a table in a cool room, the tea inevitably cools down. Heat flows from the hot tea into the cooler surrounding air until eventually the tea and room reach the same temperature. The reverse never happens by itself. A cold drink doesn't spontaneously absorb heat from a cooler room and become hot. In fact, heat flows naturally from warmer objects to colder ones, and not the other way around. This one-way tendency is formalized as the second law of thermodynamics. In a gentle, everyday sense, it means that nature tends toward balance or equilibrium. Differences in temperature, pressure, or any kind of order will even out over time unless you do something to maintain them. A hot object will cool, a cold object will warm. They seek a common middle ground. You can think of it like this. If energy is conserved, first law, the second law tells us how energy flows, always from being concentrated in one place or form to becoming more spread out. It's a bit like a perfume diffusing in a still room. Initially, the scent is strong at the bottle and absent across the room, but gradually it spreads, becoming uniform and faint everywhere. Similarly, heat spreads out and dissipates unless actively concentrated. This law introduces the concept of entropy, a measure of disorder or randomness, which tends to increase in any natural process. But rather than worry about the jargon, consider the everyday comfort it provides. Things naturally settle down into a sort of quiet uniformity. A hot cup of tea left alone will eventually become the same temperature as the room, a peaceful equilibrium. A spinning top will slow and come to rest, its energy gently released as a bit of warmth to the floor and air. The second law is sometimes poetically described as the arrow of time, because it gives a direction to processes. We can tell the movie of the tea cooling is running forward, not backward. Yet, seen another way, it's a promise that the wild differences smooth out, that systems left alone find a kind of calm. By the same token, it tells us that we can't get a perpetual motion machine, which would endlessly produce useful energy from nothing. Some energy will always escape as unrecoverable heat. Nature always takes her cut. But this too can be seen positively. It is the reason a warm fireplace heats a whole room evenly, or why a fever cools down with rest. In time, imbalance becomes balance. Amidst the formulation of these grand laws of motion, gravity, electromagnetism, and thermodynamics, physicists also study the nature of waves and vibrations, phenomena that are all around and often soothing. A wave is a repeating pattern that travels through a medium or even through empty space, and it turns out waves underlie many aspects of physics. We have already encountered waves. Light is an electromagnetic wave, and heat can travel by infrared waves. But there are also the waves we experience directly, through hearing and touch, especially sound waves. Sound is the gentle propagation of vibrations through air, or water, or solids. Consider a quiet night by a still pond. If you toss a pebble into the pond, ripples spread out in concentric circles, causing a leaf on the surface to bob gently. Now imagine plucking a string of a violin or guitar in a silent room. The string vibrates rapidly, and those vibrations pass into the air, creating ripples of higher and lower pressure that spread outward. Though you cannot see these airwaves with your eyes, if you are nearby, you will hear a soft musical note as the wave reaches your ears. The physics of this is beautifully simple. The vibrating string pushes air molecules, which then push on their neighbors, and a wave of pressure moves outward like an expanding bubble. Each tiny parcel of air only moves back and forth a little, but it passes the vibration along to the next parcel, and so on. Finally, when that wave of minuscule air oscillations reaches your eardrum, it makes the eardrum vibrate in the same pattern, and your brain interprets that as sound. All of this happens seamlessly and invisibly, allowing you to enjoy, say, the soft notes of a lullaby without ever seeing the sound itself. Like ripples on a pond, sound waves can be visualized as concentric spheres of compression moving outward from the source. In the darkness of night, you might hear the chirp of crickets or the distant hoot of an owl. The cricket's chirp is high-pitched, meaning the air is vibrating very quickly in rapid waves, whereas the owl's hoot is low-pitched, the air undulating at a slower rate. Both sounds arrive to you as gentle fluctuations of pressure. If you could see sound waves, you'd see the air very subtly pulsating. Each sound has a frequency, how fast the wave oscillates, and an amplitude, how strong the compression is. High-frequency waves, cricket chirps, feel like rapid tremors on the eardrum. Low-frequency waves, an owl's hoo, feel like slow, deep undulations. Typically, higher frequencies we hear as higher musical notes, lower frequencies as lower notes. But the technicalities aside, what's important is how comfortingly physical sound is. It's a handshake between objects and our senses, carried by the air. Even something as dramatic as thunder is just air being rapidly pushed and pulled by a sudden expansion, lightning heating the air. As the rumble reaches you, it's merely a wave spreading out and fading with distance, often heard long after the lightning flash in leisurely, rolling echoes. Waves aren't confined to water and sound. The idea of waves permeates physics. Light, as Maxwell showed, is a wave of electric and magnetic fields, and unlike sound, it doesn't need a material medium like air or water to travel. This is why sunlight can traverse the vacuum of space to warm the earth. Similarly, the heat you feel from a fireplace across the room arrives as infrared light waves through the air and can even travel with no air. Waves can also overlap and interfere with one another in curious ways. If you drop two pebbles in a pond, their ripples intersect and create a new pattern of peaks and troughs. In some places, the water might momentarily be extra high, where a peak meets a peak. In other places, nearly flat, where a peak meets a trough and they cancel out. This is called interference, and it happens with all types of waves. Two sound waves can interfere as well. If you have two speakers playing the same tone, there are spots where the sound is louder, waves adding, and spots where it's softer or silent, waves canceling. Even light waves interfere, producing beautiful patterns of bright and dark bands, as scientists like Thomas Young discovered in the early 1800s. The idea that waves can superpose and cancel was at first a strange concept, but it's an inherently peaceful one. Waves pass through each other and continue on, sometimes adding, sometimes subtracting, always redistributing energy in patterns. No permanent harm done, just a complex dance of peaks and troughs. One remarkable property of waves is how they carry energy and information without permanently carrying matter along. When a gentle ocean wave lifts you up and then down, you end up where you started. The water itself hasn't carried you to shore, unlike a current. It's the wave pattern that traveled through the water. In the same way, when sound wafts from a distant violin to your ears, the air itself doesn't blow all the way from the violin to you. Instead, each parcel of air passes the message to the next. It's like a relay race. Energy is handed off from one bit of matter to the next, but no single air molecule travels the whole distance. This is why, when you stand in an open field listening to wind in the trees far away, the breeze at your face might be still, yet the sound arrives. The pattern of pressure moves through the otherwise static air. And as mentioned, light waves require no carrier at all. They are self-propagating disturbances in the electromagnetic field, so they can move through the vacuum of space. This leads to a striking fact. In the vacuum of outer space, where there is essentially no air, sound cannot travel at all. Space is silent, utterly quiet, because sound has no medium there to ride on. If two massive asteroids were to collide in the asteroid belt, it would happen in eerie silence, an unimaginably violent event, seen from afar in complete quiet, though it might send a faint vibration through the ground if you stood on a nearby asteroid. This cosmic silence is actually comforting in its own way. We look up at the night sky and often describe it as serene and still, and indeed it is. The stars shine quietly. Even cataclysms unfold in mute grandeur. Here on Earth, we are enveloped in air, so we're used to sound everywhere, the whoosh of wind, the chatter of life, the roll of thunder. But step into the void between worlds, and you enter an enormous hush. It gives one a sense of the vast, calm scale of the universe. By the end of the 19th century, thanks to the work of Newton, Faraday, Maxwell, Joule, and many others, physics presents an elegant, reassuring framework for understanding the world. The laws of motion and gravity explain the orbits of planets and the trajectory of a thrown ball. Electromagnetic theory explains light, radio, electricity, and magnetism as manifestations of one unity. Thermodynamics provides rules for heat, work, and the inevitable increase of entropy, explaining why engines can never be 100% efficient and why time flows in one direction. The behavior of waves underlies optics, acoustics, and much more. It seemed there was a grand completeness to the physics of nature's everyday phenomena. Some even said around 1900 that physics was essentially finished, with only a few minor clouds on the horizon of knowledge. Little did they know those small clouds would herald storms of innovation. In the early 20th century, two revolutionary chapters of physics opened: relativity and quantum mechanics. These new ideas would extend our understanding to the realms of the very fast, the very massive, and the very small, revealing a universe even more surprising and subtle, yet one that remains harmonious and comprehensible. The first of these revolutions, relativity, arose from the gentle genius of Albert Einstein. Einstein, a thoughtful and imaginative young man, often let his mind wander in what he called thought experiments, essentially daydreams guided by physical principles. One of his most famous thought experiments came to him as a teenager. He imagined what it would be like to run alongside a beam of light, keeping pace with it. In his mind's eye, Einstein visualized himself chasing a light beam through space. If he could run just as fast as the light, would the wave of light appear frozen in time beside him like a still ripple? It was a playful, imaginative question, the kind one might ponder while staring at a sunset or the stars. Yet it carried profound implications. According to James Clerk Maxwell's electrodynamics, which Einstein had learned in school, a frozen light wave made no sense. Maxwell's equations didn't allow a stationary light wave. This puzzle, a seeming conflict between the principle of relativity, that the laws of physics should look the same to everyone moving at constant speed, and Maxwell's light equations, lodged in Einstein's mind. Einstein carried this gentle quandary into his adult years. In 1905, while working as a clerk in a Swiss patent office by day and pondering physics in quiet moments, he finally unraveled the mystery. The solution, startlingly simple yet deeply counterintuitive, was that the speed of light is the same for everyone, no matter how they move. Whether you are standing still or moving toward a light source or away from it, or even riding on a fast train, if you measure a beam of light zipping by, you will always get the same result, about 300,000 kilometers per second in vacuum. This constancy of the speed of light upends our common sense intuitions. Normally, if a car is moving and you run after it, its relative speed to you is less than if you were standing still. But with light, even if you could somehow chase it at incredible speed, it would still slip away from you at that very same speed of 300,000 kilometers per second. How can nature be this way? Einstein realized that space and time themselves must be flexible to accommodate this rule. In order for everyone to agree on the speed of light, they must disagree on measurements of distance and time. In the gentle equations of what became known as special relativity, Einstein showed that measurements of length, time, and mass are not absolute, but depend on the relative motion between the observer and what is observed. It turned out that if one person is moving very fast relative to another, each will perceive the other's time as running a bit slow, and lengths in the direction of motion as a bit contracted. These effects are usually infinitesimal in everyday life, because we move so much slower than light, but they become dramatic as you approach light speed. For example, an astronaut orbiting Earth experiences time passing just a touch more slowly than people on the ground. After a year-long stay on the International Space Station, an astronaut might be a few milliseconds younger than they would be if they had stayed on Earth the whole time. This isn't science fiction or mere theory. It has been measured with precise atomic clocks and was famously reflected in the story of identical twin astronauts Scott and Mark Kelly, where Scott's long mission in orbit made him age ever so slightly less than his brother on Earth. The difference was tiny, just milliseconds, but it was real, a gentle skewing of time itself. If we take a more extreme, imaginary scenario, suppose one twin got on a spaceship and traveled near the speed of light on a journey to a distant star and back, while the other twin stayed on Earth. Upon reuniting, the traveling twin might find that less time had passed for them than for the earthbound twin. Perhaps the spacefaring twin has lived 10 years, while the stay-at-home twin has lived 30. This is sometimes called the twin paradox. though it's not a paradox at all when you work through the details with relativity. What a peaceful oddity. By simply moving fast, one can literally stretch time. Einstein's 1905 theory, special relativity, focused on the relativity of uniform motion and had one more astonishing prediction. Nothing with mass can be accelerated to the speed of light, because as you approach that speed, you would require infinite energy to push further. The speed of light isn't just fast, it's a cosmic speed limit, and perhaps his most famous equation, E equals mc squared, emerged from this framework, telling us that mass itself is highly concentrated energy. Even at rest, an object has stored energy simply by virtue of its mass, a hint at the potential power locked in matter, later seen in nuclear reactions. Yet, in our calm narrative, we note this mainly as a profound unity of nature. Mass and energy are two forms of the same thing. Like different currencies with a fixed exchange rate, mass can be cashed in for energy and vice versa, though doing so typically involves violent processes like nuclear fusion or fission, far from our gentle contexts, except in the cores of stars or the glow of the sun that sustains life. Einstein did not stop with special relativity. In 1915, after a decade of further pondering and with much help from mathematics, he published the general theory of relativity, which extends his ideas to include gravity and non-uniform motion. General relativity is a triumph of insight and is often described with the image of a fabric or rubber sheet. In Einstein's new picture, gravity is not a force that reaches across space as Newton imagined, but rather a feature of space and time themselves, or spacetime, as we call the unified concept. Mass and energy tell spacetime how to curve, and that curved spacetime tells objects how to move. A popular analogy is to imagine space as a stretchy, trampoline-like sheet. Place a heavy ball on it. The sheet sags under the weight. Now, if you roll a smaller marble near the heavy ball, the marble will no longer travel in a straight line. It will spiral inward or orbit around the heavy ball, following the curve of the dented sheet. In an analogous way, the sun's mass curves space-time around it, and the planets follow paths along that curved geometry, what we perceive as orbiting the sun. Earth's gravity, in turn, is the curvature of space-time around our planet, which the moon follows, and which causes apples to fall toward the ground. In a sense, apples fall and planets orbit for the same reason. Both are moving along the invisible contours of distorted space and time. It's a hard idea to visualize fully, but the analogy of the rubber sheet gives a hint. Gravity is geometry. Einstein's general relativity was initially met with some skepticism, but it quietly proved its merit. In 1919, during a total solar eclipse, astronomers observed starlight passing near the sun and bending inward. Just as Einstein's theory predicted, Newton's gravity had predicted only half that bending. The news made Einstein famous worldwide. Yet in truth, all of this happens without fanfare in nature. Space is gently curving around any massive object all the time. We don't feel space-time curvature as something jarring. Instead, we experience it as the steady pull of gravity. The physics that holds your body to the Earth is the same that guides planets and the trajectories of far-off galaxies.
And so, as these gentle echoes of space-time drift through the cosmos, they whisper a secret to us all. Even in vastness, everything is connected by the same peaceful laws. Imagine those ripples as a barely perceptible murmur in a grand cosmic sea, reminding us that every heartbeat here on Earth is part of a universal rhythm. Our own hearts send out pulses that travel through tissue and bone, tiny waves translating life's quiet music. In much the same way, black holes and neutron stars share their subtle song, imperceptible to our senses yet detectable by patient instruments. These discoveries invite us to rest in the knowledge that the universe's drama unfolds according to a serene choreography, planets, stars, and particles all playing their parts in a vast, harmonious dance. And now, we gently close this chapter of our cosmic lullaby, allowing the soft cadence of creation's quiet wonders to carry you into dreams. Let the faintest cosmic currents cradle you, as gravity and light weave a tender blanket around your mind. As night blankets our world, feel the serenity of the sleeping Earth, where the whispers of tides narrate tales of distant worlds. Each falling star, a reminder of the countless stories unfolding in the vast tapestry of the universe, quietly burning bright, then vanishing, yet leaving a mark on the great expanse. In our shared silence beneath the stars, we find unity, A gentle reminder that though we are many, we are one.